In this video, we're going to look at more details about our SN2 mechanism. SN2 mechanisms were our second order mechanism. Right, it stood for substitution, nucleophilic, and then bimolecular. Right, both the alkyl halide and the nucleophile are involved in the rate determining step. Since both the alkyl halide and the nucleophile are involved in the rate determining step, it is a second order mechanism. Right? Our rate law involves the concentration of both of those, right? Changing the concentration of my alkyl halide affects the rate. Changing the concentration of the nucleophile affects the rate. So both the alkyl halide and the nucleophile affect the rate of our reaction. Right? Second order, the 2 stands for that, right? Bimolecular. We're going to look a little more detail about the mechanism. So instead of writing an R like I did in the previous one, we're going to draw out an actual molecule for us. So our mechanism, remember it is concerted. Right? My bond making and breaking occur at the same time. So I'm going to break the bond between my carbon and the halogen at the same time that I form that bond. So drawing out an alkyl halide, right? Remember that that carbon is partial positive because of that bond to bromine. So that carbon is electrophilic. And then I'll have a nucleophile. We'll use methoxide, so a carbon bonded to an oxygen. I do have 3 lone pairs and a negative charge on that. And then that nucleophile is going to attack that partial positive carbon at the same time that I break the bond between the carbon and the halogen. I just want to move that partial charge out of my way because it's in my way. So my mechanistic arrows, I'm moving 2 electrons, so we're going to use our double barbed arrow, right? This is a polar mechanism. And I'm forming that bond at the same time that I'm breaking that bond. Because it's occurring at the same time, it occurs with what's called, we call it backside attack. Essentially, the bromine has to leave from the opposite side that the nucleophile adds. They can't be coming and going from the same side because they would run into each other, right? I'd have steric issues. So the stereochemistry of this, we would say it has backside attack. And this is going to be important. If that molecule was chiral, we're actually going to have an inversion of configuration, and we'll look at that here shortly. But it does occur with backside attack. So what that means is the nucleophile attacks, right, or adds, attack sounds so sinister, from the opposite side that the leaving group leaves. Right, the leaving group is my halogen in this case. So the bond that I'm forming needs to essentially be 180 degrees from the bond that I'm breaking. I am going to show a transition state for this one because it's concerted, because it takes place in one step. I do want to see the transition state. So whenever you're drawing mechanisms for me for SN2 reactions, you do need to draw that transition state. And I need to make sure that I show this right geometry when I draw that transition state. So again, the bond, I could write that here, between the bond breaking, let's say, should be 180 degrees from the bond forming in the transition state, which you do need to draw. I guess for full credit. You don't have to draw it, but you'll lose points if you don't. So again, whenever you draw an SN2 mechanism for me, I do want to see that transition state. And then when you draw that transition state, make sure that the bond that you're forming and the bond that you're breaking, which are going to be shown as dotted lines, right, because they're partial in that transition state, are 180 degrees from each other. So I'm going to draw out the actual carbon, that partial positive carbon, otherwise it looks kind of weird. There are 2 hydrogen on that carbon also. So this is that carbon. I'm going to draw a dotted line to the bromine that I'm breaking. And then 180 degrees from that, I'm going to draw a dotted line between that methoxy group, between that nucleophile. And then I'm just going to attach everything else to it. I do have a CH3 group, and you can draw the skeletal if you want. I'm just drawing it out so you can see kind of where everything is. And then because it's a just transition state, we want those brackets with our double dagger symbol. So again, make sure that this dotted line and that dotted line are 180 degrees. I drew them left and right. You could draw them up and down. You could draw them diagonal, but they do need to be 180. So however you want to make that work. And then everything else that's attached to that carbon is still attached to it. And then my product, and I'm going to draw it on the other side. This isn't a chiral molecule because I do have 2 hydrogen on that carbon, but if it was, like I said, my stereochemistry would be inverted. So my product, we did just substitute the bromine for that methoxy group. So again, right, my nucleophile attacks at the same time my leaving group leaves. Because that's happening at the same time, it needs to happen from opposite sides, meaning in my transition state, I need to have those 2 bonds 180 degrees from each other. Looking more specifically at the stereochemistry of that reaction, if it's chiral, then the configuration is going to be reversed. So if it was R, we end up with S. If it was S, we end up with R. So if the alkyl halide is chiral, the configuration is reversed. Right? We would say that this occurs with inversion of configuration. So my stereochemistry, I would say my configuration is inverted. Essentially, your highest priority group in your reactant was likely your halogen. Your highest priority group in the product is going to be your nucleophile. And because they're now on opposite sides, because of that backside attack, my configuration is going to be opposite. So looking at one that was chiral, so we'll look at the mechanism again, and then I'm going to put a methyl group on here, and then there is a hydrogen still. So it's a chiral center, right? That carbon is bonded to a methyl group, an ethyl group, the bromine, and the hydrogen. And if I was to look at its configuration, my highest priority group, number 2 and number 3. So as I go from 1 to 2 to 3, that's counterclockwise. My lowest priority group, my hydrogen, is going back. So we don't need to switch it. So that is S. I'm going to get that out of the way. And then we'll use the same nucleophile that we did before. Actually, let's put 2 carbons on it this time. So negative charge. And then drawing my mechanism, it attacks that partial positive carbon at the same time that my bromine leaves. I am going to draw my transition state. So again, I'm going to draw out that partial positive carbon. It's easier for me to see this if I actually put a C there. Since you're drawing skeletal structures, you don't have to. But again, that's just easier for me. And then that's bonded to its 2 carbons. I'm going to do a mix of skeletal and structural. And then attached to that carbon, right, I have a hydrogen. I have that methyl group. Actually, let's try to make it look more. It's kind of hard enough to do it. I'm going to have the methyl group and the hydrogen down here, since that's how I drew them in my original structure. And then I'll have my ethyl group up here. And again, you can leave that as a dot. You know, if I wanted to leave it, you don't have to draw it out. You could do this, right, with the bromine and then the ethoxy group. It's just that always looks kind of weird to me. I like to focus in on that carbon, so I tend to draw it out. Again, it's not a requirement. It's just a requirement that you draw the transition state and that you make sure that you're doing that backside attack. So my partially formed and my partially broken bond do need to be 180 degrees from each other. Since the transition, tongue-tied, sorry, because it's a transition state, brackets and my double Laker sign. And then looking at our product, and I'm going to draw it just a little bit lower so I have room to do it. I'm going to have it inverted. And you can draw this a couple different ways, but you do need to make sure that you're drawing the stereochemistry with the right configuration. So I had this group, right, my nucleophile attack, that's now bonded to that carbon that had the halogen bonded to it. That carbon is also bonded to that ethyl group, and then it has the methyl group and then this hydrogen, which you don't actually need to draw because we're doing skeletal structures. When I do my configuration now, right, this is my highest priority group, number 2 and number 3. When I go from 1 to 2 to 3, it's clockwise. My lowest priority group is back, so I don't need to change it, so R. So it was S, we now have R. If I wouldn't do the backside attack, right, if it came and went from the same side, my stereochemistry would not be inverted. But again, my SN2 reactions is always going to occur with backside attack, meaning that if it's chiral, I will always have inversion of configuration, right? It was S, it is now R. Looking at an energy diagram for this, because it's taking place in one step and I don't have an intermediate, I'm just going to see that one, I'm only going to have one activation energy, right? Just that one energy hill to get up. So my energy diagram, energy increasing on my y-axis, my reaction proceeding along my x. So I'm going to go up and then come back down. This is going to be a spontaneous reaction. So my reactants, my transition state, and my products. I just have the one activation energy because it's just one step. And then my overall energy change, I almost gave it no energy at all there, is the difference between these two. Again, our book is going to call it delta H. You could call it delta G. I said spontaneous, so I'm going to call it delta G. If we labeled it as an enthalpy change, I would say it's an exothermic reaction, right? It has less heat energy when I'm done than when it started.